Valence, or valency, is one of the oldest and most useful concepts in chemistry. Valency is the combining capacity of an atom. In simple words, it says how many bonds an atom can typically form with other atoms. Chemists observed that if one atom was taken as reference, let's say hydrogen, different atoms combine with it in a characteristic and fixed proportions. For example, chlorine combines with one hydrogen to form HCl. Similarly, oxygen combines with two hydrogen as H2O. Nitrogen combines with 3 hydrogen as NH3. Carbon combines with 4 hydrogen as CH4. From these observations, they realized that different elements have different combining capacities. Since one hydrogen atom can form only one bond with other elements, it was taken as the reference. Historically, valency was defined as the number of hydrogen atoms that an atom can combine with or replace. As we saw above, one oxygen atom can combine with 2 hydrogen atoms, so its valence is 2. On that scale, nitrogen has valence of 3 and carbon has valence of 4. At that time, the role of electrons was not known in chemical reactions. Today we know that bonding involves electrons. Therefore, in the modern context, valency can be interpreted as the number of electrons an atom loses, gains, or shares to achieve a stable electronic configuration. If studying the transformation of matter is the universe of chemistry, the fundamental question would be, why the matter even transforms? Why do atoms combine at all? If we go to the depth, this question becomes, if elements are stable identities, why don't atoms remain isolated? Why do they combine to form molecules and compounds? The fundamental idea that governs these transformations is that nature always tends toward a lower energy. Imagine a piece of pure iron kept completely isolated from all other 117 elements or their compounds. As long as nothing else comes into contact with it, there are only the same iron atoms in it, no chemical reaction takes place. The iron remains iron. Now expose the same iron to oxygen. Gradually, it transforms into iron oxide or rust. Here, what changed? The iron itself did not change. The oxygen already existed. The only new event was that iron and oxygen were brought close enough to interact. When they interact, a new arrangement of atoms becomes possible, one with lower energy than the individual iron and oxygen. Nature always tends to move toward a more stable, lower energy state whenever a suitable pathway exists. This lower in energy is the driving force for chemical bonding and chemical reactions. In other words, atoms do not combine simply because they come into contact. They combine because the bonded state is energetically more stable than the individual entities. Now, imagine placing an iron atom next to a neon atom. Even if they remain in contact for years, under ordinary conditions, they do not form a chemical bond. Iron remains as iron, and neon remains as neon. This is because forming an iron-neon bond does not produce a more stable, lower energy entity than the isolated atoms. Therefore, no chemical bond is formed. Hence, a chemical bond is a stable attractive interaction between atoms or ions that lowers the energy of the system sufficiently to hold them together. Chemical bonds are classified according to the nature of the interaction between atoms. Different ways in which atoms interact give rise to different types of chemical bonds. But how do atoms interact? An atom consists of a nucleus surrounded by electrons. When two atoms come close to each other, it is their electrons and the nucleus that mainly interact. And the resultant interaction later becomes a bond. Therefore, the nature of the interaction between atoms is ultimately determined by how they interact. Based on this, the chemical bonds are classified into four major classes: ionic bond, covalent bond, dative bond, and metallic bond.